Welcome back to the deep dive. Today we are looking deep, deep inside the atom at a process we've all heard of, radioactivity. And when you hear that word, you probably think of, you know, danger, instability.
Cautionary signs, yeah. And that's the common view, but the reality is that radioactivity is also the foundation for some of our most precise and, frankly, life-saving tools.
Right. We're talking about everything from carbon dating ancient history
to medical imaging that can see inside our bodies. It's this cosmic clock and a surgical tool, all defined by one core idea. It's a process that fundamentally changes the identity of matter.
And that change in identity is really the key, isn't it? We've got a fantastic set of sources here that get into the mechanics of this, specifically focusing on the theoretical work of Enrico Fermi back in the 1930s.
And that's our mission for this deep dive. We want to show you how Fermi's model for nuclear decay didn't just solve a huge physics crisis. It actually contained the intellectual blueprint for, one of the greatest achievements in modern physics.
Which is the unification of two fundamental forces of nature, the weak force and the electromagnetic force.
Exactly. Decades before it was proven.
That is just incredible foresight. So we're going to unpack how atoms actually change, look at the crisis Fermi was facing, and then uncover this powerful analogy in his physics. And finally, we'll see how all this abstract science helps us in the real world. Okay, so to set the stage, let's just start with the basics, how atomic identity works, because decay completely rewrites the rules.
Right, so an element's identity, what makes it, say, carbon or nitrogen, is defined entirely by one thing, the number of protons in its nucleus. That's it.
The atomic number.
The atomic number. You change that number, you change the element, period. Now, if you keep the protons the same, but you vary the number of neutrons, you get different isotopes of that same element.
Like carbon-12, which is stable, versus the one we all know, carbon-14, which is radioactive.
Precisely. Carbon-14 is unstable. And radioactive decay is just that spontaneous process where an unstable nucleus tries to get more stable by losing energy. It emits radiation.
And in doing so, it can actually change its proton count, a transmutation.
It is a transmutation. When carbon-14 decays, one of its neutrons turns into a proton. So it goes from 6 protons to 7, and poof, it's not carbon anymore. It's nitrogen-14.
The fascinating part to me is that for a single atom, it's totally random. You can't predict when it's going to go.
You can't. It's purely spontaneous. And crucially, it doesn't depend on outside factors like temperature or pressure. That's what makes it so reliable as a clock. Because when you have a huge number of atoms, which you always do, the collective decay is perfectly predictable. It follows a very precise exponential decay law.
And that law is what gives us the idea of a half-life.
Yep. The half-life is just the time it takes for half of the radioactive atoms in your sample to decay. It's a fixed number, a constant. And that reliability is everything.
A reliability that was desperately needed back in the early 1930s. Physics was in a bit of a mess after the discovery of the neutron, and beta decay was the biggest puzzle of them all.
Oh, it was a crisis, a genuine crisis.
Yeah.
Beta decay is when a neutron turns into a proton and spits out an electron. Seems simple enough.
Like a two-body problem.
That's what they thought. And if it were a two-body problem, the electron should come out with a single predictable energy every single time. It's just based on the mass difference.
But it didn't. When they measured it, the electrons had this wide, continuous range of energy.
All over the place. And that was terrifying for physicists, because where did the missing energy go? Either the experiments were wrong, or, and this was the scary part, the law of conservation of energy was wrong.
Which would just break physics.
Completely. So in 1930, Wolfgang Pauli steps in and, as he put it, proposes a desperate remedy.
He literally apologized for it, didn't he?
He did. He suggested there had to be a third unseen particle carrying away that missing energy, something neutral with almost no mass, a ghost particle.
And then Enrico Fermi takes this ghost particle idea and builds a whole mathematical theory around it.
He does. In 1933, Fermi formulates the first real quantitative theory of beta decay. He took Pauli's idea and he gave the particle its name, the neutrino, the little neutral one.
And we have to stop for this historical nugget from our sources. He writes this groundbreaking paper, and the journal Nature rejects it.
Rejects it flat out. They said it was too speculative.
Wow.
It just shows you how far out the idea was. He had to publish in an Italian journal, which slowed its initial spread. But the math was so rigorous and it just worked so well that it became undeniable.
Okay, let's pivot to the core of this deep dive. Because Fermi didn't just solve the beta decay problem. He did it by using the blueprint from a totally different area of physics.
That's the genius of it. He was a master of a technique called quantum perturbation theory, and he just used it in 1932 to describe how atoms emit and absorb photons, light.
Which is governed by the electromagnetic force.
Right, and then a year later, he applies the exact same mathematical architecture to model beta decay, which is governed by this brand new weak force.
So, wait, what exactly is perturbation theory? Is that just a way of saying he's like tweaking an existing formula?
Sort of. It means you start with a simple system you can solve perfectly, like a stable nucleus, and then you treat the complex new force, the weak interaction in this case, as a small perturbation, a tiny mathematical wiggle on top of that simple system.
Okay, so he saw that the wiggles that describe light emission and the wiggles that describe nuclear decay, they look the same mathematically.
They responded to the same kind of formula. And a key formula, now called Fermi's golden rule, gave the right answers for both phenomena. The success of the same algebraic structure in two different domains was a huge clue.
A clue that they must be connected on some deeper level.
Very deep level.
Let's try to visualize the analogy he was drawing. So, for light emission, an electron in an atom jumps from a high-energy state to a low one and spits out a photon.
Correct. So for beta decay, Fermi imagined the neutron and the proton as two different states of the same particle, the nucleon. The transformation of a neutron into a proton was just like the electron changing energy levels.
And the photon that gets emitted in the light process.
That was mathematically analogous to the electron-neutrino pair that gets created in beta decay. The whole mathematical machinery was parallel.
The obvious difference, though, is the strength. Electromagnetism is powerful. The weak force is, well, weak and very short range.
It is, and Fermi had to account for that. In his theory of light, the strength is determined by the elementary charge, E. For the weak force, he had to introduce a new constant, G, we now call it Fermi's constant, which was just a number that quantified how much weaker this new interaction was.
Now, today we know the weak force is carried by massive particles, the W and Z bosons. It's not just particles popping into existence at one point. Did Fermi's math hint at that?
I mean, this is the amazing part. He was so close. For his paper, he chose the simplest possible model, a point-contact interaction, basically to avoid being too speculative again.
He'd learned his lesson from nature.
Right. But the formalism he built, the complex vectors he used, they implicitly contained the structure of the modern theory.
How can you see that in the math from back then?
It's in the structure. The mathematical object he created to describe the nucleons, a type of four-vector, is directly analogous to the hadronic currents we use in the standard model today. It showed the underlying operating manuals, the Lagrangians for the weak, and electromagnetic forces had the same basic structure. His math was basically screaming for a heavy mediator particle, a W boson, even if he didn't put it in the final paper. The foresight was just baked into the equations.
That's just stunning. He's trying to save energy conservation in 1933 and accidentally maps out the unification of fundamental forces for the 1970s. So what does all this abstract physics actually mean for us today?
It means we can trust these decay laws with our lives and with our history. Let's start with archaeology, radiocarbon dating.
Willard Libby's work in 1946, all based on the beta decay of carbon-14.
Yep. Libby realized that cosmic rays are always creating C14 in the atmosphere. It gets into the food chain, into every living thing. But when an organism dies, it stops taking in new C14.
And its internal clock starts ticking.
The C14 starts to decay, with its very famous half-life of about 5,730 years. By measuring how much is left, you can tell how old something is.
But he had to prove it worked, right? Against things where they already knew the age.
Absolutely. He created what he called the curve of knowns. He tested it on things like ancient Egyptian funerary boat timbers.
Yeah.
And it worked. It gave us the first truly objective dating method, and it completely revolutionized archaeology.
I read in one of the sources he used it to date the end of the last ice age in North America.
He did. People thought it was about 25,000 years ago. Libby's C14 data from ancient trees proved it was much more recent, only 10,000 to 12,000 years ago. A massive shift in our understanding.
An amazing tool. Let's shift to medicine, because controlled decay is saving lives every single day.
Nuclear medicine is all about this. We use radioisotopes either as tracers for diagnosis or as tiny radiation sources for therapy.
And for diagnosis, the big one is technetium-99 meters, right?
It is. It's used in something like 80% of all procedures. It's almost perfect for the job.
Why? What makes it so ideal?
A few things. It has a nice, Short half-life of 6 hours, so it doesn't stay in the body for long, the dose is low. But crucially, it decays by emitting pure gamma rays.
High energy light.
Exactly. High-energy light that passes right out of the body and can be seen by a camera. It lets you create incredibly clear images of organs without doing much damage to the tissue itself.
And then there's the other side, therapy, using radiation to kill cancer cells.
That's where you want the damage, but you want it to be incredibly localized. So we often use beta emitters, like iodine-131, that deposit their energy over a very short distance.
The idea is to get the radioactive atom right inside the tumor.
Precisely. For thyroid cancer, iodine-131 is perfect because the thyroid naturally soaks up iodine. So the radioactive isotope gets delivered directly to the diseased tissue, destroying it from the inside out while sparing the healthy cells around it.
So if you tie all these threads together, it comes back to Fermi's genius, not just for calculation, but for synthesis.
It does. He didn't have the giant particle accelerators we have today. He couldn't see a W boson.
Instead, he just used this incredibly powerful analogy. He took the known mathematics of light, of electromagnetism, and used it to model the unknown physics of nuclear change.
He saw a common structure, a shared blueprint between the atomic world and the nuclear world, and in doing so, laid the foundation for unifying them decades later.
It's just a powerful lesson in how scientific progress actually happens. It's about seeing those deep patterns.
And here's a final thought for you to take away. The whole foundation of Fermi's model, of carbon dating, of everything we've talked about, rests on one core assumption.
That the probability of decay is constant. A nucleus has no memory. Its half-life never changes.
Exactly. We print those half-lives in textbooks as immutable constants of nature. But some recent, very high-precision experiments are showing that the decay rate can be influenced by the atom's environment.
Really? How?
Well, if you take an atom and you strip away all of its electrons, make it fully ionized, its nucleus can sometimes decay differently.
How different?
In some cases, spectacularly so. There's an isotope, rhenium-187. Normally, its half-life is 41.6 billion years. But if you strip off all its electrons, a new decay path opens up, and its half-life can drop to just 32.9 years.
Wait, from 41 billion years to 33 years? That is a staggering change. The stability of the nucleus depends on its electron cloud.
It raises a fundamental question, doesn't it? If we can change a constant of nature that dramatically just by changing the electronic environment, what else might influence these fundamental processes? That constant we thought was written in stone might just be, well, a little more flexible than we ever imagined.
Something profound to consider about the very clocks that govern the universe. Until next time, keep digging deep.